I didn't open the Blackboard page today, but but on the class Blackboard page, I did manage to create a homework folder, and so this first assignment is posted, and then there's a second assignment posted, okay, in Blackboard. However, I have a copy of this, so I'm going to give the printout to you as well, so you don't really have to print it from Blackboard, but it is there. And on the back of this is the usual graph paper, but we're going to use that today, maybe in class, okay, at some point. Depends on how far we get, right? Okay, so this is for class, and then this is just your description of the homework. So everyone who has class with me knows how I'm partial to graph paper. You can see that from the notes, right? All right. Okay, so I do want to today spend some time talking about the homework, the first homework assignment, right? Because I've had lots of people come by and ask me questions, and so for that I am very appreciative. So I really do appreciate you coming by and asking me questions. I'm not just saying that. I really do appreciate it because it really helps me think about it spurs me to think about the homework problems as well, okay? Because I do not always know immediately the answers to the homeworks, and I have to think about them too, okay? So when you come and force me to think about them, that's good. That's beneficial to me and to the class. All right, so we are going to stop at some point and talk about those. Okay, there's a lot of fun problems there, and I want to also sort of demystify the homework a little bit for you. Okay, so that you're not being too sort of cautious or careful when you're writing down your answers to the homework problems, okay? Because if you try to be too precise or too exact, you're going to end up writing down probably more than is necessary for me to see, okay? And then you'll spend a lot of time trying to perfect your answers, and that's not always necessary. Although that's good practice, so if you want to do that, that's great, okay? But it's not always necessary. All right, so anyway, but before we do the homework, I did want to talk a little bit more about some examples of combinatorial settings and problems, right? So we've only been through kind of one big example, and that was examples from chessboards, right? Okay, and tiling examples, and then, but also we mentioned a couple of examples where one is forming paths across chessboards by visiting squares on the chessboard in a particular manner, right? Okay. All right. So, but we have some other examples of again settings for combinatorics problems and examples of combinatorial type problems and thinking. So I want to get through a few of those more. It's just kind of a broad overview here, right, of how combinatorics works or what combinatorics is. Okay, so we're still kind of on the initial part of the course, and we'll see how far we get today, and hopefully we'll finish that Monday, because then we have to get into some of the more formalities of some of the more technical details of combinatorics, right? How do you actually solve these problems? What tools and concepts do we really commonly use, right? Frequently use to solve combinatorics problems, right? Okay, so that we're not just always sort of ad hoc inventing solutions to problems. But we frequently have to do that in combinatorics, okay? So there's a lot more ad hoc logic involved in solving combinatorics problems than in other maybe other disciplines in mathematics, okay? And that's what's a little bit scary about combinatorics. You often have to improvise, okay, on problems. And all problems, even when they are somewhat similar, they have some differences that kind of make them uniquely challenging. All right, so okay, I think you may have already experienced that in the first homework. All right, so but you're going to experience that a lot. Okay, so so let's look at a second big example here. So rectangular arrays, right, are like chessboards. Are common settings for combinatorial problems, but we don't have to restrict ourselves to chessboards, okay? So we often look at other types of rectangular arrays, okay? And so here's a couple of famous examples where we build grids, rectangular arrays, but we're going to fill them up with numbers, okay? But of course, we put some restrictions on, some conditions on how we put the numbers into the grid, right, into the array, okay? And that's what makes the problems interesting, all right? So some of these types of grids I'm going to talk about here, these are famous, and so you may have seen these as examples in the past, okay? They often form the basis for games, okay, or puzzles, actually. Puzzles is more like it, okay? But we are going to talk about games, too. I think a puzzle is being something that an individual would solve, right? Okay, that's kind of a game. But a game is something where you have players, okay, right? But we're going to talk about games as well, where you have players opposing each other. Okay, so a famous example here of another type of a rectangular array is what's called a magic square, okay? And so you may have played with magic squares before, seen magic squares in the past. So a magic square, they can have different sizes, but a magic square of order n, okay, is just an n by n, so it's a square, okay, array, and it's filled with numbers, all right? But of course the numbers have to follow a particular pattern, right? So what you're going to do is put in the integers into the squares of the array, right? And the integers, you have to fill up all the squares. So you're going to fill it up with the integers 1, 2, 3, etc., up to n squared, because that's how many squares you would have to fill up, right, if it's an n by n. A rectangle, correct? Okay, so you're going to fill in the square there with the numbers 1, 2, 3, etc., up to n squared. Okay, so that will completely fill up the array, but you have to do it. You can't just do it willy-nilly, right? Well, I guess you could, okay, but that won't give you a magic square. Okay, so to get a magic square from this arrangement of numbers, you have to fill in the values so that all the rows and all the columns, but also all the diagonals, well, there's two diagonals, right? So all the rows and all the columns and the two diagonals all add up to the same number, okay? That's a magic square. Have y'all heard of magic squares before? Have you ever played with magic squares? I was going to say, I'm afraid you're all going to say, oh, yeah, we're experts on magic squares. Ask me anything, okay? All right, so magic squares have been a kind of a source of amusement for people, including mathematicians, but also just, normal people, right, for a long time. And actually, so it says there, they've been studied since at least 190 BC in multiple cultures, okay? I think this original reference to a magic square from 190 BC actually comes from China, okay? So different civilizations have played with magic squares, okay? I mean, different civilizations have discovered them. I don't know if they have a common origin or not, but they show up in different civilizations. And sometimes they're associated with mythical or occult practices, okay? Or they're assumed to have some sort of magical significance, okay? Now, we're not going to use them for occult purposes in here, right? But we're just, sorry, right? So we're not going to be placing curses on your biology instructor or anything using the magic square. But but we're just going to look at their properties a little bit, okay? And again, lots of people have played with and studied magic squares. Actually, a lot of famous people have constructed magic squares. I'm talking about non-mathematicians have constructed and talked about magic squares, okay? Famous example of that is Benjamin Franklin. So, but he was kind of, he studied lots of different things, right? He wasn't, he's, I guess, most famous now as being a politician, but he was also a scientist as well, right? And a very wealthy person, by the way. Oh, he did. Yeah, okay, right. So I'm going to tell you about the role. Benjamin Franklin, was the wealthiest person in colonial America, right? So he wasn't just a nobody, because Benjamin Franklin started the postal service, and it was private, right? Huh? Oh, yeah, and the Postal Service was private, so I think he, at first, right, this was before there was a United States government, and so he made a lot of money. It was like the FedEx of colonial times, right? So he made a lot of money that way. All right, so Dalton has started the roll around. Where is it? That was fast, okay? All right, so I put the instructions on there, so if you've had classes with me before, you're familiar with how this works. So you just want to, when it comes to you, sign in the first available slot, and then remember that number, because that's where you're going to sign every time, okay? Right? So that's kind of your magic number. So write that down or put that in your phone. If it's an easy number to remember, Dalton is, did you sign 1?
I don't know, maybe it was 11.
Okay, all right. All right, so, well, you signed wrong. But anyway, remember your number because you're going to sign there each time, right? So put it as a note in your phone or something, or in your notebook. All right, so we'll try to pass that around each day, but I frequently forget, so I'll try to be good about that. Okay, that's how we're taking roll, right? Okay, so here's a magic square of order 4. So to verify this, we would have to add up all the rows and all the columns and each of the 2 diagonals, right? Okay, so I'm not going to do that, but I think that's at least the book says that's a magic square of order 4, right? Because it's 4 by 4, and we filled it up, right, with numbers 1 to 4 squared, 1 to 16, right? Okay, and now this sum that the columns and the rows and the diagonals sum up to, that's called the magic sum for the magic square. So we can see what the magic sum is here just by adding up one of these rows or columns, right, since they're all supposed to add up the same. So this is what, 16 plus 3 is 19, 21, right, plus 13 is 34, right? So we can see there the magic sum is 34, right? Okay. All right, so so to sort of give this kind of our combinatorial flavor, right, let's create a set here. So I'm just going to let set be the set of all magic squares for a particular order, all right, okay? So for a specific choice of m, okay? And so that may be the set here that we're exploring. So we may want to count that set, right? Okay, so we may actually try to determine its cardinality, okay, as we discussed last time, what it means to count a finite set, right? Or we may just be, as we frequently are, right, we may just be interested in showing that this set is empty or non-empty, right? We may want to show there's nothing in this set for a particular choice of n, or at least there's one thing in the set, right, for a particular choice of n, okay? Well, so I've already shown here that when n is equal to 4, m is non-empty, right? It has at least one element in it because there is a magic square of ordered 4, right? Okay, so we've demonstrated that m is not empty, at least when n is equal to 4, okay? All right, now it turns out actually m is usually quite large, actually, right? The size is quite large, except in one case, all right, which we'll talk about here. All right, so if n is equal to 1, right, okay, that means you have a 1 by 1 grid, and so there's only one way to create even a square, right, of that order, right? So there's your 1 square of order 1, and that happens to be a magic square just by default, right, okay? All the rows and the columns are all the same there because there's only 1 row and 1 column. They all add up to 1, and the diagonals are all the same, right? You know, if you even want to think of that as having a diagonal, it also adds up to 1, right? So there's 1 square of magic 1. Okay, well, that's kind of boring. Okay, now we're going to talk a little bit later. Actually, you're going to show me that there's no magic square of order 2. So there's not a magic square of order 2. All right. But as the order gets larger, then you start getting lots of magic squares. So if n is 3, it turns out there are 8 magic squares of order 3, okay? And that's going to be one of your homework problems from the second set of homework, okay, is to actually figure out that there are 8 squares of order 3, okay, 8 different ones, all right? If n is 4, it turns out that there's 8 times 880 magic squares, and if n is 5, then there's this many, all right, okay? So there's a huge number, right? Who knows what that number is, right? Okay, but a really big number if n is 5. That's known exactly. But these numbers get really large really fast. So when n is greater than or equal to 6, actually the cardinality of m is not known. All right. We don't actually know how many magic squares there are of orders larger than 5. Okay, well that's kind of interesting. All right, it's just because there's a lot of them. So there's lots of. It seems like there wouldn't be that many ways of, sort of solving this puzzle, right? But it turns out there are trillions, I guess, right? Ways of filling in these different ways of filling in these magic squares. So it's really not hard to create a magic square. Okay, and that's why lots of people have done that. Well, when I say it's not hard, okay, that's a little bit misleading. There's a lot of them, but it still might be hard to. Might be challenging to create one. Okay, if someone just gives you that chore, so maybe we're going to try that. All right. Okay. Now, usually the sort of the fundamental idea here that you can use to discover things about the size of that set M, all magic squares of a particular order, is to notice that the magic sum is fixed. Okay, so for a particular choice of n, that is for a particular order, it's not that you can have lots of different magic sums. It's always the same magic sum for that order. Okay, it's just a matter of how do you fill in the squares with those integers 1, 2, 3 up to n squared, so that the rows and the columns and the diagonals add up to that magic sum. But you can figure out what the magic sum is quite easily. Okay, and I'll show you how to do that. All right. Okay. All right. So first, we're going to fill in, right, we're going to fill in our magic square. If we choose a particular order, right, we're going to fill in our magic square, right, with these integers, correct? 1, 2, 3 up to n squared. Now, if you sum all of those integers up, it's easy to compute what the sum is going to be. Okay. So if you add up 1 plus 2 plus 3 plus up to n squared, it turns out that this is what the sum is. It's going to be n squared times n squared plus 1, and then just divide that by 2. Okay, let's talk a little bit about why that's the case. So just a little bit about why that's the case, because that's based on a really famous formula from arithmetic that we're going to use probably frequently in the course. Okay, so do y'all know this formula that I'm using here? If you take the first k positive integers and add them up, all right, there's an easy formula to compute that. Okay, so you don't have to add one by one to sum up the first k positive integers. It's always going to be k, whatever k is, times 1 more than k, and then divide that by 2. Have y'all seen that formula before? Okay, or you may not remember it exactly, but you may remember seeing that, okay, in the past. All right. So so here, right, we're adding up a positive integer starting at 1, but we're going up to n squared. Okay. Well, that's still the largest in our series, right? So so the sum is going to be n squared times 1 more than n squared, and then divide that by 2. Okay, so this just comes from this famous formula, which we're going to see again in the class, actually perhaps as soon as today. Okay, all right, because that's a very useful shortcut for adding up the first few positive integers, right? And turns out that that sum appears quite frequently, okay, in lots of different problems. All right, now, okay, so if we were to take the entire magic square and just add up all of the squares, which is usually not what we're doing, right? We just want to add up a row or a column or a diagonal, right? But if we were add up all of the squares, we would get this sum, right? N squared times n squared plus 1 divided by 2. Okay, now, but if we have a magic square, let's imagine that we have a magic square, right? Well, we know, right, that all of the rows have to add up to the same value, right? Okay, because it's a magic square. So pretend here that this is a magic square. I haven't filled in the columns here, right, but there are the rows, okay? And we know that the rows always add up to the same value, right? That's the magic sum. So I'm going to call the magic sum here S. All right? So all of these rows if you add up to across, right, they would always add up to S. So if you add up all of these row totals, correct, that would give you the total of all of the squares in the magic square, right? Okay. So if I add this row's sum to this row's sum to this row's sum to this row's sum to this row's sum, right? That would give me the sum of everything in the magic square. Is that correct? Right? See what I'm saying? If I add up, say I add up across here, I know that has to give me the magic sum, right? Because all the rows have to be the same value. So I'm just calling that S. I don't know what that is yet, right? Okay. But then if I add up all of those row totals, that would give me all of the squares, the sum of all of the squares in the magic square. But when you add up all of these row totals, what do you get? Well, each of these row totals is what? I'm pointing at it there, so say S, right? Okay. So you take S plus S plus S. How many times are you adding S together? Well, you have n rows, correct, right? Because this is a square. So you just get n times S as the sum of all of the row totals. But that's the sum of the entire magic square, right, of all the squares in the magic square. So you know that n times S, correct, okay? Add up all those row totals. That has to be the sum of everything in the magic square. But we already said that's going to be n squared times n squared plus 1 divided by 2. All right, so see, now you have this nice equation involving S. That's the magic sum. So you can solve for S, just divide both sides by n. And so what do we get there pretty easily? Okay, we get n, not n squared, but n times n squared plus 1 divided by 2. So for a magic square of a particular order, that's what the magic sum always has to be. Did that work for this example here? Of course it has to, right? But let's just verify that. So here was a magic sum of order 4, right? And we already had looked and counted, right, that the magic sum was 34. But according to our formula, what's that magic sum supposed to be? It was going to be the order, which is 4, times 4 squared plus 1, and then you divide that by 2. Ooh, does this work? So this is what, 4 times 17 divided by 2, so that's 2 times 17, which is 34. Yay! Okay, so there we at least verified the formula for that particular example. But that's true for no matter what choice of n, no matter what choice of order that you have, okay? And that turns out to be a really useful fact in helping you prove things about magic squares or create magic squares, right? All right, so here's our first little question here, okay? So here's a gimme question for a test. If n is 2, right, and if you're going to create a magic square of order 2, of course I actually already told you that there aren't any magic squares of order 2, right? But if we were going to create a magic square of order 2, then what would the magic sum have to be for that magic square? So what's the S value? What would that have to be? So what was our formula? You take 2, right, and then what? Yeah, 2 squared plus 1. Y'all are ahead of me, so you've already calculated there. It's what? 5, right. Okay, so if we had a magic square of order 2, then the magic sum would have to be 5. Okay. What about for 3? All right, what's the magic sum going to be? Pretty easy here, right? So 3 times 3 squared plus 1, and then we have to divide that by 2. Gosh, I hope that always comes out divisible by 2. That's a question in itself, right? So this is what? 3 times 10 divided by 2, which is 15, right? Okay. All right. So so for magic squares of order 3, which I claimed there were 8, okay, there are 8 different such magic squares. Well, we know the magic sum at least. That's got to be 15, okay? So if you were trying to build a magic square of order 3, all right, one of those 8, then that's a clue that you could use to help you, right? You would know that the magic sum has to come out to be 15. So when you're arranging your numbers in your rows and columns, you sort of keep that in the back of your mind, right? Those always have to add up to 15. All right. All right. Can just take a few minutes here, and you can talk with your partner. See if you can convince your partner and yourself at the same time, right? That there is no magic square of order 2. Okay. So you can convince yourself however you want of that fact, okay? There is no magic square of order 2. But you can use, I don't think you have to use, but maybe it's helpful, you can use that the fact that the magic sum would have to be 5, right? Okay, so does that help you convince yourself that there's no magic square of order 2, all right? So if you convince yourself of that, try to convince your neighbor, okay? So just annoy your neighbor there and say, hey, there's no magic square of order 2. Here's why. Okay, and then we'll share here in a minute or two. So practice this with yourself, right? So try thinking about this because this type of thinking is going to show up in the homework where there's some questions about magic squares, right? So it's good to have practiced it a little bit before you get to the homework on a simple example like this one. Did I get my, did I get the roll here squared away? Okay. Oh. So did someone else miss? Kaylee? Okay, sorry, Kaylee. Anybody else did not sign it? All right. So if anybody comes in, we probably won't have any late comers now, but if anybody comes in late, ask them to remind them to sign the roll. Okay, so anybody want to share why they think there's no magic square of order 2? Okay. Want to share their reasoning with that? Don't be shy here, okay? Oops. So a lot of people look like they're thinking about it. You want to share yours? Yeah, what's your reasoning there? Oh, okay. So you're claiming just sort of by sort of exhaustive analysis here, right? There's only 2 ways of even putting the numbers in there, or what?
Well, 2 ways of doing it so that the diagonal numbers are, the diagonal can either be like 1 and 4 or 1.
Oh, I see. Okay, right. So the diagonals have to add up to 5, right? Okay. So you could have what? Well, I guess 1 and 4 and 3 and 2 on the diagonals, right? That's what it has to be, right? Something like that?
Yeah.
So what's one arrangement that would give us that?
So 3 different ways.
Okay, all right. So
there's diagonal of 1 and 4.
diagonal of 1 and 4, right?
Yeah, and then the other diagonal would be 2 and 3.
2 and 3, right? But I guess you could put the 2 and the 3 in different spots, right? Okay. So so we could put the 2 here and the 3 here, but neither one of those is going to, that's not going to work, right? Okay. And then you would say, okay, another possibility would be what? 1 and 4 and the 3 here and the 2 here, and still not going to work, right? Okay. And then what's our other option?
1 and 3 for diagonal.
No, 1 and 3 on a diagonal won't work, right?
Yeah,
Yeah, right, okay.
that way. And that's, like, those are the...
I guess we could maybe think of this as being different, right? 4 and 1, or or we might think of having the 4 and 1 here, right? Okay. Um, that's right. Yeah. Okay. I think. So can you think of some way of maybe shortening that argument?
Well, I mean, I'm just saying that since there is.
I think you're correct, right? So you've just you've just sort of analyzed the different possibilities, right? Okay, and none of them going to work. Okay, so that's called a sort of an exhaustive analysis, and that's perfectly fine. We solve many combinatorics problems exactly that way, okay, by just looking at the different possibilities, okay? So, yeah, I think that's great, okay? I'm convinced. Dalton, were you going to say maybe a shorter way of explaining this?
Yeah.
What would you say?
Well, I just did by row just because it was a little easier, I guess.
Oh, I see.
Easier, but just like, so top left corner start with 1 because 1 has to go somewhere.
Mm-hmm.
And the only way to get 1 to add to 5 is to have a 4.
Oh, okay.
So
Right.
you have like 1 and 4 in the top row, and then you can't make any more valid moves because the column for 1 will never be able to equal 5.
Right. Okay.
And
Yeah.
so you're kind of stuck.
Yeah, that's sort of the argument that that's sort of a shorthand version of your argument, right? You could say, oh, the 1 has to go somewhere, right? Okay, so let's say it goes here, okay? Of course, you could put 1 in other places, but I think the arguments will all be symmetric, right? So if you put 1 here in the corresponding row, you must have a 4, right? Okay, but once you've got 1 and 4 here, then you're not going to be able to make this diagonal add up to 5, correct? Right? Okay, so that would sort of give you a shorter version of that same argument, right? Okay, so I think that's pretty easy to convince ourselves. Okay, unfortunately, no magic. Well, I don't know if it's unfortunate, but no magic square there of order 2. All right. Okay. Now, you're going to, as I promised there, you're going to count. The 8 magic squares of order 3. That's in the homework. Okay. So maybe a good place to start that is just to find 1 magic square of order 3. Okay. All right. But we're not going to start with that. Okay. Because I'm going to give you a little hint on this homework problem, okay? And this hint is in the text, okay? But I'm going to show you how this hint comes about, all right? I think, okay? Oh, we're going to try to do this, all right? So let's see if I can make this work. All right. So I claim now that this fact is true. If you have a magic square of order 3, the middle has to be 5, okay? So the only way to make a magic square of order 3 work is to get the middle to be 5, okay? And then once you know the middle is 5, I think that's the key there to help you understand why there's only 8. There are some magic squares of order 3, but there's only 8 of them, okay? Because the middle one must be 5, I claim. Right? So the only way to get this is to put the 5 in the middle, all right? Okay, now let me see if I can remember why this is the case, all right? So, and I'm using the book to help me here because they actually explain this. All right, so let's suppose that we have a magic square of order 3, all right? So if we have a magic square of order 3, then we already calculated before that the magic sum has to be what? There it is right there. What? 15, right. So we know S is 15. Okay. All right. So, but I don't know what the squares are supposed to be, right? So we're going to use a little bit of algebra here. Boy, algebra sure comes in handy all the time. All right. So I'm just going to label the values in the squares by variables. So I'm going to try to make it somewhat systematic. So I'm going to call the first row ABC and the second row XYZ, and the third row is a little bit less artful there, but that's going to be D, E, and F. All right. So of course we know, right, if you add up ABC or XYZ or DEF, right, or AYF or DYC there, right, those have to add up always to 15, okay? So I'm going to create some of those sums, all right? But I'm going to try to do it in just a very artful way. So let's look at this diagonal, All right, so that's this diagonal from the top left to the bottom right. So that's a plus y plus f. And we know that has to add up to what? 15, right? Okay. And now let's look at the middle column. So that's b plus y plus e, right? And that has to add up to 15. All right. Now, you may wonder why I chose the middle column to pick on. Well, there's a reason, okay? You're going to see here in just a second. All right. So now let's look at this diagonal, the one from the top right to the bottom left. So that's c plus y plus d, right? But still 15, correct? And then I'm going to look at the first row. So that's a plus b plus c, that's 15. And then finally, the last row, that's d plus e plus f, which is also 15, right? Now, I could add up different rows and different columns and throw in more equations here, okay? But I only need these 5 equations, I think, all right? What a relief, okay? I don't need more equations than that. All right, so here's what I'm going to do. I'm going to add these 2 equations together. So y'all have to help me do this because I haven't done this before. All right. So I'm going to add these 2 equations together. So you know how you add equations together, right? You add the left-hand side and the right-hand side, right? And then you just make those 2 sums equal, correct? So if I add up these 2 left-hand sides, right, it has to add up to these 2 right-hand sides, correct? Right? So what's that going to be? Can I write all that down? That's what? A plus b plus c plus d plus e plus f. Is that right? And those are all different variables, right? So I don't have to combine any variables. I don't have any like terms. Is that right? And so what does that add up to, of course? 30, right. Now, I'm also going to add up the first 3 equations, okay? So, wow, what do I get there? All right, now this will have some like terms, so y'all have to help me with this. So I'm going to add up the first 3 equations. Do I get what? A plus b plus c plus, and then I get y 3 times, right? So I have 3y, and then what? D plus e plus f. Actually, f plus e plus d, but I'm going to write it as d plus e plus f. And is that right? Is that what I get when I add up these 3 equations? Yeah, I think that's true, right? And so, but what does that add up to? 45, right, okay? So that's very convenient. That adds up to 45. Now, what do you notice about, though, those 2 equations? Yeah, they all have what? They both, there's only 2 of them, right? But they both have what? A plus B plus C, right? And they both have D plus E plus F. Is that right? Okay. So, that's cool now, right? So now I can subtract this equation from this one, right? Okay, so I'm going to subtract this one from this one. Okay, so can I just write that down? I'm going to subtract this equation from this top equation. I'm sorry, the bottom equation from the top equation. And of course, what does that leave me with then? There you go, right, okay. You get very nicely there, just 3y is equal to 15, or y is equal to what? 5, right, okay. So very easy, right, okay. So you know that the middle square has to be 5, okay. So anytime we build so we don't have that many options, right, or this at least restricts, right, the options for a 3 by 3 magic square. The middle square has to be 5. Okay. All right. So in your second set of homework, right, you're going to get to experiment with y. Then that means there's only 8 magic squares of order 3, okay? Anybody see one already? Is anybody out there already monkeying with that, okay? If you know the middle square is 5, okay? All right. Now, I'm going to show you one way here. This is described in the book, and all right, so this one is okay, this does require some practice, but you will get some practice with this, okay? I'm going to show you just a method, a routine, right? Actually, an algorithm that you can use to build a magic square for any odd order, okay? All right, so there are lots of, as we mentioned, lots of magic squares, right, of different orders, especially as the order gets large, right? You get tons and tons of magic squares. So there are sometimes systematic methods for building magic squares, and here's a famous one due to the Frenchman de la Lubert. So let's cut off the de la and just call it Lubert's method here, all right? And so I'll show you how this works, okay? It's really cool. All right, so, but this only works for odd order, okay? So, all right, so you'll have to watch me here. But this is described in the text, this system, on the bottom of page 8, okay? So, so I think in the homework they're going to ask you to use this same method to build a magic square of order 7, maybe of order 9 also, okay? But I'm going to practice here with order 5. All right, so, all right, but there are some rules here, okay? So but it does require practice. All right, so, but the first step is really easy. You're going to go to the top row, and since this is odd, right, the order has to be odd. This only works when the order is odd. So you're going to go to the top row, and since the order is odd, you're going to have exactly a middle square, right? Okay. So in this case, the middle square on the top row is right there. All right. I guess you can vary this in different ways and come up with slightly different magic squares by placing the 1 in a slightly different spot. Okay. And then running the algorithm, say, in a sort of symmetric fashion, but not quite the same. But here's the classic description. So we're going to put a 1 right there. Okay, all right. So you got 1, all right, out of all those. Okay, and again, you know there's a middle square there, right? Because this only works when the order is exactly odd, right? Okay. Now, all right. The way de la Lubert's method works is you start filling in up the diagonal to the right. Okay. From this number, just counting, all right? Of course, since you put a 1 here, though, there is no diagonal. There is nothing to put right there, correct, right? So when that happens, you just flip to the bottom row, okay? You just flip to the bottom row and continue, all right? All right, so the 2 will get placed here, all right, as though this row were actually above this one. So you just sort of cycle around, right, okay? And the same thing happens when you're moving up and to the right, because you always move up and to the right. The same thing happens when you move up and to the right and you run out of columns on the right. You just revert to the first column, okay, as though the first column were following the last column, okay? So you sort of think of this as kind of a circle, right? All right, so the 2 is going to get here. Do you understand that? Because I would like to put the 2 there. There's no square there, okay? So I revert to the last row as though this row were on top of this one. All right, so the 2 goes here. I think I've got this right. I guess we're going to find out when we get finished with this if we have a magic square. All right, now you just proceed up and to the right always. So the 3 is going to go here, okay? Now we've run out of columns, so guess what we're going to do? You're going to pretend the first column is really the last column, right? So where would the 4 go? Right here, correct, right? As though this column were really positioned over here. So the 4 goes here. And now things get, you can proceed, right? Except, so you put the 5 here, right? And now you want to put the 6 there, correct? But that is full. So what do we do? Okay, well, when you reach a full square, okay, you continue below, exactly the same, below the last square you filled in, okay, right? So when you hit a filled square, you add the next number below your the last number you filled in. So what was the last number we filled in? See, we're trying to fill in the 6, right? What was the last number we filled in? 5. So I put the 6 here, okay? There I put the 6. All right, so now things are kind of all nice here, right? So 7, 8. Oops, I want to go there, but I can't. So where does the 9 go? Right here, right? Okay, you pretend that that row, the bottom row, is really above this one. So you put the 9 here. Now I want to go up there, but I can't. So where does the 10 go? Below the 4, right. You treat this column as though it were adjacent here, right? So the 10 goes here. Oops, I want to put the 11 here, but I can't. So where does the 11 go? Below the 10. The last number we filled in was the 10, right? Now you put the 11. Ooh, that's nice, right? Because now we're going to get finally a diagonal we can fill up, right? So here we get 12, and then 13, and then 14, and then 15, right? Okay. And now I've hit the top right hand square. Okay. All right. Now, normally, right, you would say, okay, I'm going to treat this, right, as though it were. I'm going to treat this column as though it were the last column. But that won't help you, right, because you can't fill in here, right? Okay. So when you hit the top right hand square, the next number will go below below the last number that you filled in, right? Okay. So what's the last number that we filled in here? So the 16 goes here, all right? That's where the 16 would go. So so there's 2 times where you follow that rule of filling in below the last number that you filled in, right? It's if you hit a square that's already occupied, or if you hit the top right-hand square, okay, then the 16 will go here. Now, where does the 17 go? Right there, correct, right? Now, where does the 18 go? Here, right? Okay, because I would treat this column, right? Okay, I'm sorry. I would treat this row as though it were the top row. So the 18 goes here, 19, 20. Now, where's the 21 go? Because I can't use this one. Under the 20. So the 21 goes here, and then the 22 goes there, and then where's the 23 go? Over here, right? And then there's the 24, right? And I can't fill in there, but where's the 25 go? Right here? Ah, there you have it. All right. So I think that's it. That's Lubert's magic square. Is that really a magic square? What's the S here? Oh, it's 65, okay? So if you compute the S as 65, you want to check something here and see if that adds up to 65? You want to check the diagonal? Surely it can't be 65, right? 22, 35, 56, and 9. Oh, darn. Okay, that's 65, right? Does this column add up to 65? I mean, this row add up to 65? That's 29 and 25. What's 29 and 25? 64, 66, oops, and whoop. 54, okay, 56 and 65. All right. So, well, all right. So there's at least one row and one diagonal. Yeah, what?
How did we choose where to put the 1?
The 1 always, so I think you can still use Lubert's method by putting 1 in maybe a symmetrical place, but the way at least the text describes Lubert's method is it will go in the top row in the middle position. And since the order is odd, this only works for odd order, you know there is a middle position. There's an exact middle position, okay, on the top row, right? So here the middle position is this one, right? Because there's 2 squares to the left and 2 squares to the right, okay? That's how the 1 starts. Okay, there's the description of that. So again, the written description of that is in the book. What page did I say there? 8, right. Okay, so I think there's a couple of homework problems where they want you to use Lubert's method again to build a magic square. Okay, all right. But there are other types, as I mentioned, of problems on grids. So we're going to look at some not magic squares, but another type of square built on a grid called the Latin square. Have y'all heard of Latin squares? All right, so Latin squares are a little bit easier to create, okay? They're extremely useful in experimental design, so they have important applications. Magic squares are more of games, all right, okay, or occult, if you're into that. But Latin squares actually have much more important applications, and because they show up frequently in certain applied problems, okay? But they're a little bit easier to create. So usually we like to make variations on Latin squares because just a traditional Latin square is easy to devise. Okay. All right, but let's talk about Latin squares then in just a second because I want to talk about our homework and we're running out of time. So, let's talk about the homework then. Okay. All right. So now I've had people ask me questions about homework problems, so I know that some of y'all have made progress on the homework. So let's talk about some of the homework problems and see if some people want to ask about the homework problems or share solutions to the homework problems, and then also tell me what their difficulties were with particular problems, because again, I want to try to make the homework a little bit less intimidating to work on. All right. So so the first one there says, so this is a show type problem, right? So formally in mathematics, that would mean prove, okay, something. But we're not going to always be, I'm not always going to expect you to write down formal proofs for these problems, okay? So, so many of you have had theorem proving classes, and so you have some experience with writing down formal proofs, okay? And which is great, and but I'm not always thinking in the homework that you have to write down a formal proof. What I'm really interested in you getting is what is sort of the key idea. Describe to me what is the key idea that's kind of fundamental to if you were to write down a formal proof. So if you can give me just a convincing explanation, right? Convincing explanation. In a sense, that's what a proof is a convincing explanation, right? But if you can convince me with sort of the key idea as to why something is true, then that's sufficient for the homework, okay? So in most cases, all right? So you don't have to worry about getting all the words correct in a formal proof, okay? All right, so... so let's talk about that first one. So you have again, just a chessboard, right? But it's an arbitrary chessboard. It doesn't have to be a classical 8x8 chessboard. So it's n by n, right? And so what this problem asks is show that it has a perfect cover, right? With dominoes, just like we've been discussing here. If and only if one of the numbers is even, okay? It could be both of them even, right? But at least one of the m or n has to be even, all right? Okay? All right. Now, that problem contains the phrase if and only if, right? Okay? So you do have to interpret the if and the only if, right? And so the easy way to do that, right, is to just read the sentence in two directions, okay? It's saying if one of those is even, right, okay, right, then if either m or n is even, then you have a perfect cover, okay? But the other way has to be true as well, all right, which is if the chessboard has a perfect cover, if the chessboard has a perfect cover, then one of M and N has to be even. Okay, all right. So there really are two sides to this problem. All right. The first side, maybe the easier side, is showing that if one of M or N is even, then the chessboard has a perfect cover. All right. Okay. The other side is if it really does have a perfect cover, right? If it does have a perfect cover, then um, either you have to have an even number of rows or an even number of columns, or possibly both. Okay, right? So if you are able to put a perfect cover on that, then one of those two dimensions has to be even. Okay. All right. So let's see if someone can share with us just an explanation of that first thing that I mentioned there. If one of the dimensions, either M or N, is even, then why do we know that the chessboard has a perfect cover? Okay, so again, don't have to explain to me formally, right? Okay, but can you somehow demonstrate at least, right, that this thing has this must have a perfect cover if you either have even number of rows or even number of columns. Okay, can someone have an idea of that? Okay, yeah. All right. So I'll let you. What is your name again? William. All right. So William. So can you explain that to us? Do you want to draw?
I don't know if it would be helpful.
Well, it would be helpful to me. Okay, I think so, because I think I'm going to have to see that illustrated. All right. So let's let me block the projection here for a second, and we'll let you use the board. Okay. So and I've got some pins here, so we can so you can write. All right. All right, William. So tell us what you're thinking there.
Okay, so what I was thinking is I kind of looked at what would happen if they were both odd. Well, first, I guess.
Okay, but all right. So all right. So but let's go backwards. I think thinking they're both odd is a different situation. Okay.
Yeah.
Because what I was interested in is if one of them is even, right? Okay, then we have a perfect cover, right? Okay.
All right. Well, so we know that each domino has an area of 2 by 1.
Right. So it has two squares in it. Correct.
So
Right.
therefore, a perfect cover has to be a multiple of this area because there's an standing amount. So if the area of this is 2 by 1, then we have a cover. I don't know. So there's an integer amount of those. Then this goes to 2k. So the area is going to be an even number.
Okay, so all right. So what you're claiming is then that we have to have an even number of squares, right? Okay.
To be a perfect cover.
Yeah. So to have a perfect cover, we have to have an even number of. There has to be an even number of squares, right? Okay. All right.
Okay, and then so we can see that if M or N is even, so I guess we can just say that M is even,
All
then
right.
then there exists, yeah, so there exists, yeah, whatever. So M is even, so then we can calculate the area of an N by N chessboard.
Okay, so, all right, so let me explain a little bit why that's not completely convincing.
Okay.
All right, okay?
All right.
All right, so, but it's a good start. All right, so I think what William is saying is um, we would have to have an even number of squares, right, just to get a perfect cover, correct, right? Because each domino is going to cover 2 squares, right, okay, right? Each domino is going to cover 2 squares. You have to have a whole number of dominoes, so you're saying, imagine that's k, right, okay? So if you get a perfect cover, right, you're going to cover 2 times k, right, squares, right? That is an even number because it's a multiple of 2. Right, okay, yeah. So you have to have an even number of squares. I agree with that if you're going to have a perfect cover, correct, right, okay? All right, now, you're saying, though, if one of these is even, right, okay, say it's m, so m is even, so it's a multiple of 2, right?
Yes.
Yeah, that's the correct way of expressing that. So you're saying if m is even, right, then it's a multiple of 2. So m times n would also be a multiple of 2, so that's even, right? Okay. All right. So, but see what you've actually shown me there, William, is just that there is a chance, right? Okay. There's a chance that the chessboard has a perfect cover, okay? But just saying there's a chance that it has a perfect cover doesn't really mean that there is one, right? Okay? You're just saying it's possible if one of these is even that there's a perfect cover. But I actually have to not know just that it's possible. I have to know that it actually happens, okay? See, it's a difference between something may happen and something definitely happens, right? Okay? Right? Okay, so it's not just that it's within the realm of possibility that there's a perfect cover. It's a definite certainty that there has to be a perfect cover. So the way to demonstrate that is to actually sort of demonstrate to me what that perfect cover would be. So you have to sort of give me a method of actually covering the chessboard in this case. There may be multiple methods, but you just have to give me one of when one of these is even, right, okay, then there is a curve cover. All right, but, oh, you can do that? Okay, yeah, I think you can, right? So actually, let's try that. So you already said, let's assume m is even, and then if n is the one that's even, maybe we could run a very similar argument, right? Okay, so kind of draw a picture for me of a m by n chessboard, right? Okay.
So if we have chessboard,
Yeah, if that one runs out, try this one. This may be better.
so if, let's say, this side is n and this side is m.
Right.
Okay, so if m is even.
If m is the even one, right?
Yeah, then we can just stack some dominoes like this all the way until we get to the bottom of the chessboard.
Oh, that's right, right. And that will now that's going to, those dominoes now stacked vertically will perfectly cover the first column. Why is that?
Because m is even.
Because m is even, right. So actually, William, how many dominoes do you need to cover the first column?
We need,
I, right? Okay. Right, okay. Because you said m is 2 times I. Each one of those dominoes will cover 2 rows, right? Okay.
Yeah.
Correct, right? And so you just need I dominoes to cover the first column. All right. So we got the first column. Now, how do we continue that covering?
Well, since this length here, is just 1,
Right.
then you can just have n number of them.
Oh, that's right. Yeah. Okay. So you just sort of repeat that same idea for the second column, right?
Yeah.
There you go. Right. Okay. Perfect. Right. Okay. Now, what if? Now let's see if the symmetric argument is true. So, what if n is the one that's even? Then, how does our covering look? Draw maybe a separate picture there. Oh, okay, all right. Oh, so just turn the, just rotate the chessboard. Is that what you're saying there?
Yeah.
Okay, just rotate the chessboard and do this again?
Yeah.
Oh, all right, okay, I'll accept that. All right, so rotate the chessboard 90 degrees, right, and then repeat this idea. Okay, perfect, right, okay. So, yeah, that's correct, right. So if one of the two is even, then we have the perfect cover. What's kind of a really simple way of saying this? If the number of rows is even, that's M, right? If the number of rows is even, then how do we build our cover? Yeah, that's right. Okay, we fit all the dominoes in vertically, right? Okay, and if it's the other way, if n is even, then how do we fit our dominoes in? Horizontally, right? Okay, we fit the dominoes in horizontally. Okay, all right. So that's kind of the really short way of explaining that. Okay, that's what I would accept for the answer to number one. Okay, so that's not really a formal proof. Williams, what he wrote down is much closer to a formal proof. Okay, but just the idea there, I think, is enough to, I think, convince anyone, right, that you have a perfect cover if one of M or N is even. Now, but if you have a perfect cover, okay, right, so suppose that I'm not building the perfect cover. Suppose someone showed me, here's a chessboard. It's got a perfect cover, okay, and there it is, all right. So you can see the perfect cover. It may be any sort of arrangement, but it's a perfect cover. Then why do you know that either M or N is even? Okay, Lee, yeah. So
use the contrapositive, then you can say that if both M and N are odd.
So Kaylee's saying, well, let's suppose that neither one of them is even, right? Okay. Then suppose that means that both M and N are odd, right? Then what's your explanation?
Then you can, what did I say? We are left with an odd number of squares, and thus it's not a multiple of 2, and therefore there will always be one square left uncovered.
Okay, so if both M and N are odd, then the number of squares in the area is, you're claiming, also what? Odd, right, okay. I think that's true, right, because the product of two odd numbers is odd, right. Yeah, the product of two odd numbers will be odd, okay. So if both M and N are odd, then the number of squares is odd. But if the number of squares is odd,
it's not a multiple of 2.
It's not a multiple of 2, so what? We cannot have a perfect cover, that's right, okay, by 2 by 1 dominoes, right, okay, as William just showed us, right. If you have a cover with 2 by 1 dominoes, then you have to have an even number of squares, right, okay? But if both M and N are odd, then we have an odd number of squares. So that means then that one of those two, or maybe both, but one of them has to be even, right, okay? So that's the other way to argue that, all right? Does that make sense? So now, you've sort of heard that. So if you didn't have the argument before, now maybe you can write this down, okay, right, for your homeworks, all right? Okay. All right, let's try the next one. I think this one maybe is a little bit easier. So, all right. So let me erase Williams. Whoa! Did I bring a? No, that is a whiteboard pen. Huh? No, it is. That is that's a dry erase marker, and so is that one. So don't know what's going on there. Okay, well, let's look at it here. All right. So let's look at the second problem. So where's the second problem there? Right. Okay. So here we're going. Oh boy, this one is great. All right. This was a great problem. All right. So suppose we've got an n by n chessboard, right? But both are odd. So we already know that we cannot have a perfect cover, right? Okay, of that chessboard. We know that from problem number 1. So we're going to try to fix that problem. Okay. So here's what we're going to do. We're going to take a white square. Right, so we're assuming that the squares are colored here, right, as they would be in a chessboard. But it's a white square anywhere on the chessboard. Now, just to make sure we understand how the chessboard is colored, we'll assume that the top left-hand square is white, okay? And then we'll alternate from there, all right? So you've got this colored chessboard. Now, from anywhere on the chessboard, I guess including that top left-hand square, right, we're going to cut out a white square, all right? We're going to cut out a white square. Now, that will be one less than an odd number of squares, so we will end up with, when one is removed, we will end up with an even number of squares, all right? So at least we have a chance, as William explained, right, that we will have a perfect cover. We have a chance of that, right, because we have an even number of squares left. When we take off one of the white squares, actually, if we took off one of the black squares also, we'd have an even number of squares, all right? So we have a chance here that we have a perfect cover. But now this problem says it's really not just a chance, all right? We actually do have a perfect cover, all right? So can we demonstrate, in this case, a perfect cover? Whew, wow, this one is challenging, right? Okay, so to demonstrate here, right, we actually have to show, right, or explain how we can build, right, a perfect cover of this reduced, pruned, I'm sorry, that's the right word, right, or occluded chessboard, okay? All right, does anyone have a scheme for doing this? Anyone figure out how to do this? What? Okay, so can you show that to us here? All right. All right. I don't know. Did the blue erase? I think the green pen is just old. Okay. So, but that is a whiteboard pen. So, all right, well, we'll have to just work somewhere else, all right? So, yeah, try using the blue for us, all right? So, okay.
So, on a whiteboard, you have two different colors of squares.
Mm-hmm.
In an odd case, make this one up, I suppose. I'm not going to make this one up. It's not going to look pretty.
All right.
So, this is white. The way it goes is that we'll have this checker pattern, and
Mm-hmm.
in an odd case, the last one will also be white. Black all through here. Basically what I'm getting at is that there will be one, whatever you start with, you'll have an extra one at the end of that won't pair with its black counterparts, and so we'll have, normally in this chessboard we would have 13 white squares and 12 black.
So we have one more white than black is what you're claiming if M and N are odd?
Yes.
Oh, okay. Okay, so that I think I can buy that, right? Because here's why. You're starting with a white here, right? Okay, so the first column is going to have one more white than black, right? Okay, but the second column will have one more black than white, right? So in the first two columns they'll be even. The whites and blacks, and then this happens again, right? So if you have two more columns, they're paired perfectly, right? Okay, but you have an odd number of columns, so the last column is going to leave you with an imbalance, right, between blacks and whites, and but since that's an odd column, that will be white, right? And so you'll end up with one extra white, right? So does that kind of make sense there? Okay. So y'all may have thought other ways of explaining that, but you get one. Actually, you might just count the number of whites and blacks, but you get. All right. So now what?
So we know that if we prune exactly one square, there's not an illegal way for us to put. Like we will never have to cover that hole. It's not something we have to do.
Mm-hmm.
So we can eliminate anywhere on this board, and it'll be okay.
So you'll get the same number of blacks and whites,
right? So we'll
right?
Go down to 12, or we'll go down to the same number as blacks and whites, and then they're paired. And a domino must cover a pair of a black and white, and so we have the same number of pairs, and we have no illegal covers, so it has a perfect color.
I'm not convinced.
Okay.
Yeah, I think you've done the same thing that William did, okay? I think that you have demonstrated that it's possible, right, okay? Because each domino will cover a black and a white, right, okay? Each domino will cover a black and a white. You have a corresponding number of whites and blacks when you cut off one of the whites, right? So at least that is, it's in the realm of possibility that we have a perfect cover. But you haven't actually quite convinced me that there is one, right? Okay. So you haven't actually shown me what that perfect cover would be. All right. So it's possible that there is one, and this problem claims that there definitely is one, but I think all you've convinced me is we have a chance that there's one, right? Okay. All right. So what's your name? Sean. All right, so I got multiple Seans here. All right, so but Sean, let's think about this. So I'm going to cut this one off. Let's just cut that one off, right? Because that's one of the whites, right?
Yeah.
Okay, so I'm going to cut that one off. Okay, what's the perfect cover there? You can't really draw it nicely, but just try to explain as best you can there.
So you can cover these two, these two, these two, these two, these two, these two. Pair this, that.
Whoops.
And then this, and this.
Oh, okay, right. So you clearly stuck one in there, right? Okay. So all right. So there's at least one in that case, right? Okay. But remember, m and n can be any odd values, and you can take the white off anywhere on the board. So we've looked at one of many, many different cases, right? Okay, and so we need some scheme that guarantees, right, that I can, or that you can tell me, and that I can use, right, to actually build the perfect cover, right? Okay, so not just that there is a perfect cover, but you know, how do you fit that perfect cover in there, right? Okay, no matter where I choose that, white. Yeah. Okay. Does that sort of make sense, right?
Yeah.
So it's a lot more. It's really a lot more complicated problem, right? Okay.
So,
Yeah.
I think maybe use the definition of odd numbers.
I think actually look at the definition of odd numbers is really going to help here, right? Okay, but I think look at some examples of chessboards like this one. 5 by 5 is actually really useful. Okay, and take off some white squares and see how to fit in that that cover. Okay. Oh, we're out of time again. Darn it. Catherine showed me her scheme yesterday, which is very nice for doing this. Okay. All right. So Catherine has a scheme. I came up with a slightly different one, Catherine. So I have a different version of this also, right? Okay. All right. So we won't collect homework now because I want to give more chance to talk about the first homework, right? Okay. Because I want everyone to have their chance to talk about the problems, and then we'll turn those in. So let's be aiming for Monday. I was going to say one other thing. I forgot what it was. Oh, on this problem, remember, it's just m and n are odd, right? So what's the easiest case of this? It can't be 1 by 1, because I can't do that, right? What?
3 by 3.
Well, I think even simpler than that, right?
1 by
1 by 3, right, okay? So don't get too ambitious, right? Just start by 1 by 3, and then 3 by 3 is very instructive too, okay, right? And so look at some very small cases. 5 by 5 is helpful, right? 3 by 5 might be helpful too, and see if that can clue you in, okay? All right. Thanks. Y'all didn't stop me in time. Y'all are so patient with me.